Hybridization in organic compounds. sp, sp2, sp3, sp3d2 or d2sp3 or sp3d or dsp3. So these are all the various types of hybridization of these orbitals. Let me consider s orbital that has at the most 2 electrons and they are accommodated in a box like this. It's mere representation, a single box. P orbital, it has px, py, pz. So each can have 2 electrons. So 1, 2, 3, 4, 5, 6. So at the most it can accommodate 6 electrons. Similarly, d orbital, it has 5 boxes here and each can have 2. So 10 electrons can be accommodated in d orbital. That is dxy, dyz, dxz and dx squared minus y squared and dz squared. So these are the 5 orientations, you can say. And f orbital can have 14 electrons at the most. It means there are 7 boxes and each box it can have 2. So 14. Now, you know very well, S, P, D, F, all these orbitals are of different energy levels. Assuming that energy is going up, so S orbital, P orbital, D orbital, F orbital. So they have different energy levels. But when there are some incoming entities or that is elements in order to form a compound, they reorganize themselves in such a way 1s and 3p can combine together and achieve orbital degeneracy. That is, they have equal energy level even though they are of different nature, and that is why in this case it is called sp3 hybridization orbital, sp3 hybridized orbitals. And similarly, if it has s and 2p, then it is sp2, and if it has s and p, then it is known as sp hybridization. Let me explain further based on the example methane. So methane has a sp3 hybridization. So we got 1 carbon and 4 hydrogen. So when the carbon in its ground state, it can have the electronic configuration 1s2, 2s2, 2p2. So it is represented in the box model as one box having 2 electrons, another box having 2 electrons, then 3 boxes that represent the p electrons. Of course, we have only 6 electrons, so it can have 2 electrons in the outermost orbital. And we have hydrogen, so each one can have 1 electron. It means there are 4 hydrogen. So we need to provide some space or seating arrangements in the methane, in the carbon. So they get adjusted themselves, and by the approach of these 4 hydrogen, the carbon gets excited and they form, that is, this s2 electron jump over to the p orbital and makes like this. And the electrons of hydrogen are represented here by the downward red arrows. So we can provide 1 electron in each box so that the sharing can take place comfortably and they attain equal energy level even though they are of 2 different orbitals, different types of orbitals. So it leads to sp3 hybridization. And based on the hybridization, the structures are determined. So for sp3 hybridization, we have the tetrahedral structure with the carbon hydrogen bond angles 109 degree 28 minutes. So it is as though that is a carbon is fixed in a tripod. Okay, so it has the tetrahedral arrangement. Then, and if an organic compound has only CC single bond, then you can declare that it may have sp3 hybridization. Now, let us move up to sp2 hybridization. In this case, we have C double bond C as in the case of alkene. So it has triangular planar structural arrangement. Let us consider ethene C₂H₄. So CH2 double bond CH2. So here CH double bond CH. So it means it has sigma bonds, CH sigma bond 1, 2, 3, 4. And there is one sigma bond here in the C double bond C. So your double bond consists of one sigma bond and one pi bond. And this will be this CH2 with the double bond is triangular planar. And this one will be, that is in the triangular planar, but it is vertical to the the plane of the paper. That is, this CH is above the plane of the paper and this CH is below the plane of the paper. Of course, they occupy the triangular planar structure. As I already mentioned, a double bond essentially contains sigma bond and pi bond. Let us try to understand the difference between the formation of sigma bond and pi bond. Sigma bond is a result due to the linear or axial overlapping like this. Let me consider px. They can combine like this to form sigma bond. And pi bond is due to sidewise overlapping of orbitals. So let me combine these two. So you are able to get a dark bond like structure, and that is pi bond. So the sigma bond is stronger than pi bond because the extent of overlapping is more in the case of sigma bond than that of the pi bond. Let me explain. For example, this is one px orbital and this is another px orbital. Now they can combine and the extent of overlapping is more, it's greater in the case of sigma bond. But what about pi bond? It is a sidewise overlapping. So the extent of overlapping is less, and that is why when there is bond rotation, there is a chance of breaking of pi bond, and that is why it is weaker. But in the case of sigma bond, it can be easily rotated without any breaking. And you have C double bond C with sigma bond and pi bond. So sigma bond is due to, that is, linear overlapping or axial overlapping, and pi bond is due to sidewise overlapping. In the case of alkynes, C triple bond C. So here, that is one sigma bond and two pi bonds. Its structure is linear and the hybridization is sp. And the carbon bearing two double bonds will also behave like sp hybridized triple bond. Okay, right. Now let us discuss a few problems based on hybridization. What are hybridization states of each carbon atom in the following compounds? CH2 double bond C single bond O, CH2 double bond CH CN, CH3CH double bond CH2, CH3 twice CO, and C6H6. Now let us proceed with the solution. The CH2 double bond C double bond O is written here. Here the double bond is present in the first carbon atom, so it is sp2 hybridization. And it has a two double bonds, so it is on par with the triple bond. So this can be sp hybridized. Second question, CH2 double bond CHC triple bond in actually. So you must ensure the tetravalency of carbon in each position of the carbon chain. So in the first position, CH2 plus 2, 4. So 2, 1, 3, 4 and 1 plus 3, 4. So based on that you can work out. And here it is sp2 hybridized because double bond. Here also sp2 hybridized because double bond on the left side. Whereas this is triple bond because it is C triple bond N, so sp hybridized. And then CH3 CH double bond CH2. Here CH3 all are single bond, so sp3. CH double bond, so sp2. CH2 double bond, so sp2. Then CH3 twice CO. Here CH3 C CH3 double bond O. So this can be further elaborated, and you can find this contains only single bond, so sp3 hybridized. This is also sp3 hybridized, whereas this contains double bond, so it is sp2 hybridization. In fact, you can further develop the structure like this. CH3 can be put like this. Okay, so in this case all are single bond, and that is why we have put sp3 here, double bond sp2. In the case of benzene, it is coplanar, so all these CH bonds are arranged in a single plane. So this is simply represented like this with alternative double bonds. They are called conjugated double bonds. So now let us further expand this structure, and there you may find sp2, 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 sp2. So all carbons are sp2 hybridized because every one of them has, that is, double bond. Now let us move to the next question. Indicate sigma bonds and pi bonds in the molecules. C6H6, C6H12, CH2Cl2, CH2C double bond, CH2, CH3NO2, HCONH, Now let us proceed with the solution. You know, benzene is represented by this hexagon with alternate 3 double bonds, and it can further be expanded like this. Now just count the CH sigma bonds and CC sigma bonds. It has 6 each, totally 12 sigma bonds, and there are 3 pi bonds on the double bond. So 12 sigma bonds, 3 pi bonds are present in benzene. Then C6H12. So it is not given clearly whether it is cyclohexane or alkene because it has the common, that is a formula CnH2n. So assuming that if it is alkene, then you can write the alkene 1, 2, 3, 4, 5, 6, and ensure the that is hydrogen, that is the valency, the tetravalency of carbon, and then here you can put the double bond being alkene, so C6H12, and this is nothing but one hexene. Suppose if it is cycloalkane, then it can be cyclohexane, and that also has, that is 6 Cc sigma bond and 12 CH sigma bond, so totally 18 sigma bond, where it doesn't have any double bond. But in the case of hexene, it has one double bond, and therefore you have to count the CC bond sigma bond 5, CH sigma bond 12, so CC pi bond 1. So totally there are 17 sigma bonds and 1 pi bond in one hexene. Next, CH2Cl2. CH2Cl2 is nothing but methylene chloride, that is dichloromethane. So methane is CH4. In place of 2 hydrogen, we have 2 chlorine. So dichloromethane. So this can be represented by the structure CCClHH. You have 1, 2, 3, 4. So 4 sigma bonds. That is 2 CH sigma bond and 2 CCl sigma bond. So totally 4 sigma bond. And CH2 double bond, C double bond CH2. So here you have, that is CC sigma bond 2 and CH sigma bond 4. So totally 6 sigma bonds, and there are 2 pi bonds. And CH3NO2, that is nitromethane. So CH3 N double bond O, and you have got a coordinate bond that is represented by an arrow. A pair of electron is donated by the nitrogen to the oxygen. So in this case you have 1, 2, 3, 4. Though you have 1, 2, 3 CH sigma bond and 1 CN sigma bond and NO sigma bond and NO pi bond. Whereas this is dative bond. So it is a donor acceptor bond, okay, a coordinate bond. So we have now 5 sigma bonds and 1 sigma bond in nitromethane. Now let us proceed with HCONHCH3. HCOOH is called formic acid, also called methanoic acid by IUPAC nomenclature system. So HCO double bond OOH, this is the structure of formic acid, and this formic acid can react with ammonia, where H and OH can form water, so that you are able to get amide. So this is called methanamide, HCONH2. It's also called by IUPAC as formamide. So here, this is by trivial name, and this is methanamide is IUPAC name. Now HC double bond O NH2, and it can combine with the CH3Cl. So HCl is removed. So you have got N-methyl substitution. So in order to indicate the methyl group is substituted through nitrogen, we put N-methyl, then methanamide. So that is the compound given here. So N-methyl methanamide. This is methyl group and amide group here. So Cn is 2, CH sigma bond 4, NH sigma bond 1, CO 1, CO double bond 1. So totally 8 sigma bond and 1 pi bond. Okay.